So now there is one more way that we can compute limits that is helpful in some instances. And so it's based off the following observation, or fact, I guess. And so we have the following theorem. If f of x is less than or equal to g of x, when x is near a, and the limit as x approaches a of f of x, and the limit as x approaches a of g of x both exist, then the limit as x approaches a of f of x is less than or equal to the limit as x approaches a of g of x. Now, this should not be a surprising fact. All that we're saying here is if f of x is smaller than g of x when we get really close to a, then whatever the limit of f is approaching, it's smaller than what the limit is that g is approaching. And so graphically, kind of the picture here is we have this function. So we have some function f of x and some function g of x. And as we approach the value of a, f of x is always less than or equal to g of x, so its limit is going to be smaller as well. And so we want to make use of this fact, then, to get the following result. And so this is called the squeeze theorem. So with the squeeze theorem, we have if f of x is less than or equal to g of x, is less than or equal to h of x, when x is near a, and the limit as x approaches a of f of x is equal to the limit as x approaches a of f of x, h of x, I mean, is equal to L, then the limit as x approaches a of g of x equals L. So now what the squeeze theorem is saying is that the function g of x is in between f of x and h of x, and it's getting stuck between the two of them in the limit. And so graphically, what's happening here is the following. And so we have some function f of x that's doing something like the following. We have some function h of x, which is doing something like the following, where our point A is going to be right here, just to make that clear. And so in the graph, notice that f of x and h of x, which I did not label, this is h of x, this is f of x. In the limit, as we go towards the point A, these two functions have the same value. And so this value right here is L. But now what's happening is g of x is between these two. So g of x can be doing any number of things, but as we go towards L, towards A, I mean, it's forced to stay between h of x and f of x. And so the only value g of x can take on is that same value. It's stuck between the two of them. And so since it's stuck between the two of them, its limit must be the same value. It's getting squeezed between the two. It's the idea, and it's forced to have the same limit value. Now, this idea of the squeeze theorem is particularly helpful when computing limits that deal with trig functions, because trig functions kind of have nice bounds built into them. So we're going to look at the following example. So we're going to take the limit as x goes to 0 of x squared sine of 1 over x. So we're going to compute this limit. And so now, to compute this limit, we haven't really dealt with trig functions, is what we've talked about before, but we do know a fact about trig functions, specifically sine. We know that sine of any value theta is between 1 and -1. So since that's true for any value theta, it is also true for sine of 1 over x. So sine of 1 over x is between -1 and 1. And so now if I multiply everything in this inequality by x squared, which I can do since x squared is always positive, I get negative x, well, always non-negative, I get negative x squared is less than or equal to x squared sine of 1 over x is less than or equal to x squared. And so I have a relationship now, an inequality with 3 things in it. And that's the same setup we have in the squeeze theorem. We have an inequality with 3 things between it, and the thing we want the limit of is between 2 other things. But the limit as x goes to 0 of negative x squared, that's a polynomial, so we just plug 0 in, is 0. And the limit as x goes to 0 of x squared is also 0. So the 2 things on the end are both going to 0. And so by the squeeze theorem, the thing in the middle also goes to 0. So by the squeeze theorem, the limit as x goes to 0 of x squared sine of 1 over x must also be 0, because it got squeezed between these 2 things that we knew were going towards 0. And now the squeeze theorem is helpful when we can get these nice bounds, which the nice bounds are kind of built in when you are dealing with trig functions. When you're not dealing with trig functions, it's a little bit harder to find uses for the squeeze theorem, but you can still create this situation if you're careful in forming your inequalities.